Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on the topic of computer networks. Today's topic will be on application layer. Application layer, as we all know, is the topmost layer in both the TCP/IP model as well as the OSI model. So, with respect to the application layer, we will take a look at the application architectures and requirements. We will also look at application layer protocols. Specifically, we will be looking at the HTTP protocol, which is used on the World Wide Web. So, if you look at application architectures, there are basically three different models that we talk about. One is the client server model, the other is a peer to peer model or a P2P model as we refer to it, and the other is a hybrid of this client server and the P2P model. So, we will just take a look at each of these models now. If you look at the client server architecture, what we have is we have a client talking to a server which is located on some other network. So, in a client server architecture, the server is what we refer to as an always on host, which means it is switched on all the time and the client can contact it at any time. The server typically has a permanent IP address, so that any client can contact that particular server, and the server farm, and sometimes we use server farms for scaling. A farm basically refers to a number of servers connected together. This is to handle the large volume of client requests that may come. Clients, on the other hand, in a client server model, they are devices which communicate with the server, and they may be intermittently connected, meaning a client is not permanently connected to a server. Whenever it needs a service, it connects to the server, and it may have dynamic IP addresses as opposed to a server which may have a permanent IP address, which typically has a permanent IP address. So, the client, when it requires a connection, may get an IP address assigned to it dynamically. Using that address, it contacts the server, and once it has finished its job of getting a service from the server, it may also release the IP address that it has. And clients typically in a client server architecture do not communicate directly with each other. That is, a client does not directly talk to another client, it only talks to the server. This is a typical model that we have in a client server architecture. On the other hand, if we look at a pure peer to peer architecture or a P2P architecture, here we talk about clients talking to other clients. As you can see, I have a end device, a desktop machine talking to another desktop machine, or a laptop talking to another desktop or a laptop, and so on. Okay. So, that is the kind of architecture that you have in a pure P2P architecture. So, in this case what we have is there is no always on server as in the case of the server client server architecture. So, arbitrary end systems communicate directly whenever they need to, whenever they have a need to communicate, and the peers are intermittently connected and they may change IP addresses. Example is Gnutella, which is a highly scalable. Typically what the problem with P2P architectures is that they are a little difficult to manage. They are highly scalable, which is their major advantage, but they are difficult to manage. The other type of architecture is the hybrid of client server and P2P architecture. So, that is we are trying to get the best of both worlds, the client server architecture's advantages as well as the P2P architecture's advantages. Example is Napster protocol, which uses both. It is typically a P2P architecture, but also uses the client server model for certain aspects. So, file transfer essentially gets done using P2P, but the file search could be centralized. So, peers register content at a central server, and the peers queries the same central server to locate the content. Once the content is located, they can contact the respective peers and get the files transferred from them. So, this is an example of a client server and a P2P model. Another example is that of instant messaging. If you look at the way messaging gets done, whether it is there are many service providers who provide us the messaging service these days. So, if you look at messaging, typically what we do, we chat with our friends using the instant messaging service that is available. So, chatting between two users is typically done using P2P, but the presence detection, that is detecting the presence of a person, location, all these are centralized. So, the users registers their IP addresses with a central server when it comes online, and the user contacts central server to find IP addresses of their friends or buddies. So, once they have contacted, then it is a P2P connection that takes place, but otherwise it is a centralized connection. So, this is an example of how you could use both a client server and a P2P model together. Now, typically when we look at any of these application programs communicating with one another, what we are actually talking about is an application process communicating with another application process. So, processes are communicating with one another. So, what is a process? We can look at a process for our purpose here as a program running within a host. So, within the same host, two processes could be communicating, in which case they will use some inter-process communication as defined by the OS. But when processes in different hosts communicate, they do so by exchanging messages. So, typically when we look at any application layer protocol, what we would be looking at is how the application processes are communicating with one another and what is the kind of messages that they exchange for this communication. So, that is what we will be looking at. So, when we look at processes communicating, we talk about a client process and a server process. So, client process is a process that initiates communication, server process typically is a process that waits to be contacted. Remember that when we talk about a client server model, we are talking about a server process which is always on waiting to be contacted, and client process when it requires a service connects to the server. So, that is what we are talking about over here. So, a server process is a process that waits to be contacted, and a client process is a process that initiates communication when the requirement arises. So, applications with P2P architectures actually have both client processes and server processes, which means a P2P, when I look at a P2P process, that application for instance, that application may initiate a communication in which case it acts as a client process, or it may provide a service to another process in which case it acts as a server process. So, a P2P application typically will have both a client process as well as a server process running on the same machine. Okay. Now, if we look at how these applications basically use the network services, they do so using an application interface called sockets. So, let us look at what we have here. So, you have a process which is your application layer program which is developed by some application developer. Now, this process uses the network services through what is called as a socket. Okay. So, socket we say is the application interface between the application and the network's services. So, on a given machine, a process communicates to say the TCP protocol or UDP protocol through these sockets, and of course, the TCP from one end to the TCP to the other end, the communication takes place via the internet, and on the other end again it is the same socket interface which is used for connecting up to the process. So, if you look at the process development, you can say it is developed by the application developer. TCP, buffers, variables, all these things, they are controlled by the OS. This is part of the network stack which is provided on any given operating system. So, these are provided by the OS, and using a socket you are able to access the services that are provided by the OS for network related operations. So, as an application programmer developer, what we need to know is how to interact with the socket, or rather how to use the socket to be able to send data as well as receive data on the other end. So, taking a look at what these sockets actually are, okay, these as I said, processes send and receive messages to and from the socket, that is it sends message to a socket and receives message from the socket. So, what is a socket? Basically it is something which is similar to a door, it is analogous to a door. So, that is sending process shoves message out of the door, and a sending process relies on the transport infrastructure on the other side of the door which brings the message to the socket and the receiving process. So, if you look at this example, this process just puts the message into the socket and it relies on all this rest of this process to make sure that this message is sent to the other side socket. Okay. So, the sending process relies on the transport infrastructure on the other side of the door which brings message to the socket at the receiving process. And the receiving process, as we can see, it will receive the message that has been sent through the socket again. Okay. So, when we talk of an application interface, there are basically a couple of things that we need to understand in terms of what this application programming interface, the API, should actually provide for us. With respect to sockets typically, and the API gives you a choice of the transport protocol that is used. So, remember that this is the process or the application is sitting right above the transport layer. So, and we have a choice of protocols available at the transport layer. So, choosing between TCP or UDP is something that needs to be done as to which protocol is to be used. So, which is why we say choice of transport layer protocol is one of the aspects of the API, and ability to fix a few other parameters. Again, it would depend on whether we are using UDP or TCP. So, typically we talk about UDP sockets and TCP sockets. So, a UDP socket is something which is used when you want to talk to a UDP, when you want to use UDP protocol. TCP socket is used to introduce a CCP protocol. Now the question that comes up is, how does an application choose what kind of service it requires or what kind of transport service it requires? So we just talked about having a UDP and a TCP as two different transport protocols which could be chosen by the application. How does the application decide as to whether it should use UDP or the TCP protocol? To take a look at that, we need to know the kind of services that are provided by UDP and TCP and what is it that the application expects. So if you look at what the application expects, there are three aspects that we need to look at. One is data loss, that is, some applications they can tolerate some loss. There are other applications which require 100% reliable data transfer. Example of application which can tolerate some data loss are audio related applications. Typically when you are speaking, even if there is a loss of about say a few bytes of data, you will still be able to recover the data. On the other hand, if you are looking at an application like file transfer, a file is being transferred, or a telnet application, every single byte needs to be transferred to the other side. So you need 100% reliable data transfer. So data loss is one aspect that we need to look at. Second aspect to look at is timing. So when we talk of timing, what we are talking about is what is the timing or what is the delay that is there in the data transfer. Some applications, for example, internet telephony, interactive games, they all require very low delay to be effective. If the delay is very high with internet telephony or interactive games kind of applications, you will find that you do not get the desired behavior. So timing is important in certain applications. Third is the bandwidth. Some applications, for example, multimedia, they require a minimum amount of bandwidth to be effective. Other applications make use of whatever bandwidth they can get. So these applications are referred to as elastic applications. Elastic in the sense that they will use whatever bandwidth is available. There is no minimum requirement that they have, but whatever bandwidth is available, they will make use of it. Whereas applications like multimedia, they require a certain minimum amount of bandwidth in order to be effective. So all these three parameters need to be considered, that is data loss, timing and bandwidth. So when we look at data loss, timing and bandwidth, we need to look at whether a UDP protocol or a TCP protocol is able to provide the different range of services that we are looking for. So we know that a UDP protocol is a connectionless protocol and it is not a reliable protocol. So if you are looking for 100% transfer of data, that is you cannot have a data loss, and obviously you can't go for a UDP protocol. But TCP protocol is a connection oriented protocol and will give you reliable data transfer. So then you should go for a reliable data transfer. So we go for TCP protocol. But TCP protocol on the other hand can be slow. So if you are looking at speed of data transfer, then you may go for UDP protocol. And with respect to bandwidth, again it would vary. So we need to choose based on what kind of an application it is, whether it could use UDP or whether it should use TCP. So let's take a look at a few examples and see how which protocol is actually being chosen by some of the most commonly used applications. So look at these applications: file transfer, email, web documents access, real-time audio video, stored audio video, interactive games, instant messaging. So let's look at the characteristics of these applications in terms of data loss, delay and bandwidth requirements. So if you look at data loss, file transfer, no loss, requirement is no loss. Email, no loss. Web documents, no loss. Real-time audio and video, they are loss tolerant. So you can afford some loss, afford to have some loss. Same thing is true for stored audio video, which is also we say is loss tolerant, and interactive games again are loss tolerant. Instant messaging, no loss typically. Now if you look at bandwidth, file transfer, email, web documents, they can all have and they can all use an elastic bandwidth, that is they do not have any minimum requirement, they will use whatever bandwidth is available. But if you take real time audio and video, audio requires about 5 kilobit per second to 1 megabit per second minimum bandwidth. Similarly, video would require about 10 kbps to 5 megabit per second minimum bandwidth. Stored audio video is the same as real time audio video. Interactive games, a few kilobits per second at least you need to have. Instant messaging can do with elastic bandwidth. So time sensitivity of these applications, if you see, file transfer, email and web documents, we know they are not time sensitive, but any of the interactive applications, all of them will be time sensitive. So which means that your real time audio video, stored audio video, interactive games, instant messaging, all these are typically time sensitive. But the sensitivity with respect to time, again for real time audio video it is of the order of hundreds of milliseconds, stored audio video few seconds, Interactive games, hundreds of milliseconds. Instant messaging, in fact it is both time sensitive and not time sensitive, in the sense that you can deal with some amount of delays, but it is not that you cannot have any delay at all. So, you would like to have some delay can be tolerated, but no delay would be preferable. Okay. So, that is the kind of application requirements that we have. So, given these application requirements, we need now choose the protocols. So, we will take a short break now and then come back and continue with the details. Welcome back after the break. We are just looking at the requirements of applications in terms of data loss, bandwidth and time sensitivity. So, now based on this requirements, we need now choose whether a particular application will use the UDP protocol or the TCP protocol as its transport layer protocol. So, if you look at the same internet applications, there is email, remote terminal access, web, file transfer, streaming multimedia and internet telephony. Let us look at which is the application layer protocol that is used and the corresponding transport layer protocol. Email uses an application layer protocol called SMTP. Remote terminal access, we use a protocol called Telnet. Web access, we know that we use a protocol called HTTP. File transfer uses a protocol called FTP. Streaming multimedia, typically it is proprietary, example real networks and so on. Internet telephony also could be proprietary. If you look at the underlying transport protocol, now you can see that email, remote terminal access, web, file transfer, etc. all these require reliable data transfer, and they are not sensitive in terms of time. So, they go in for a TCP protocol. Streaming multimedia on the other hand could use TCP or UDP, typically it uses UDP. Again, internet telephony typically uses UDP because it cannot tolerate delays, it requires it can tolerate loss but cannot tolerate delays. So, depending on whether it is delay tolerant or whether it is loss tolerant. So, now we have internet telephony is an application which is loss tolerant, but it is not delay tolerant. Therefore, what we do is we use UDP protocol when we are using the internet telephony application. So, next we will look at what an application layer protocol actually does. So, an application layer protocol basically defines types of messages which are exchanged. For example, request and response messages. Normally we talk about something called a request response protocol, in which case requests are sent from a client to a server and the server responds with some messages. So, it is a request message followed by a response message that you have. So, when we talk of an application layer protocol, we define the first thing we define is the type of messages exchanged. Second thing is the syntax of these message types, that is what are the fields in each of these messages and how these fields are delineated. That is, how is it that you identify the beginning of a particular field and the end of a field. Third is the semantics of the fields. What is the meaning of the information that is carried in these fields? So, all these things are defined by the application layer protocol. The fourth more important thing, in fact one of the very important things of a application layer protocol is rules for when and how the processes send and respond to messages. So, when does a particular process send a message and when does it respond to message? All these are defined by the application layer protocol. So, if you look at typical application layer protocols and how these application layer protocols are defined, we see that many of these application layer protocols are defined in what are called as RFCs. RFC stands for request for comments, and now RFCs typically are standards that are used now for defining these protocols. So, in fact, most of the network layer protocols, network related protocols are all defined as RFCs. RFC basically stands for request for comment. So, when a protocol is initially proposed, it is put out as an RFC saying requesting for comments, and so which means it is free for other people to try out these protocols and send in their comments. So, once the comments come in and the kind of the protocol stabilizes, that RFC itself becomes a standard for that protocol. So, which is why we will find that whenever we talk of any application layer protocol or any network related protocol, we refer to the corresponding RFC. The RFC is the standard for the protocol. So, most of the application layer protocols, especially the public domain protocols, they are all defined in RFCs. And these public domain protocols allow for interoperability because there is a common standard that is followed by any vendor who is implementing it or any application developer who is implementing it. It allows for interoperability between different vendors and application developers. So, example of such public domain protocols are HTTP, which is used for web access, SMTP, which is used for mail transfer, and so on. There could also be some proprietary protocols which are used for P2P file transfer and so on. There are many examples of proprietary protocols as well. What we will now look at is the most common application, which is the web access, and how the HTTP protocol provides support for this web access. Okay. Let us just look at some jargon first. A web page, we generally say, consists of some objects. Now, this object can be a HTML file, it could be a JPEG image, it could be a Java applet, it could be an audio file or anything. Now, we are all familiar with HTML with web pages, which consist of these different objects. So, we say that a web page consists of a base HTML file which includes several referenced objects. So, each object is addressable by a URL. So, example of a URL would be something like www.someSchool.edu/somedepartment/pic.gif. So, this could be the URL where this www.someschool.edu would be the host name and the rest of it would be the path name. So, when we have a HTTP protocol running, what is it now? This HTTP protocol is a request response protocol. So, when you have a HTTP protocol running, what happens is a PC or some device which needs to initiate a communication, which means to request a particular or get a particular web page, basically sends out what is called as a HTTP request to the server. Okay. So, now this PC may be running a client program, for instance may be running the Internet Explorer. Okay. So, Explorer becomes the HTTP client and the server which is running, say, the Apache web server or whatever, that becomes the server process. So, you have a client process here talking to a server process using the HTTP protocol. So, this sends HTTP request, gets back a HTTP response. On the other hand, I could have a Mac machine which is running a different client program, which is the Navigator, but this also uses the same HTTP request response. So, this server can talk to either a PC, an Intel based PC, or a Mac machine using the same HTTP protocol. Okay. So, the server need not worry about what is the machine over there, it only needs to worry about whether it is using the HTTP protocol or not. Okay. So, that is the idea that is used. So, this HTTP, we all know this, it stands for Hypertext Transfer Protocol. So, it is web's application layer protocol and it works in the client server model. So, the client is the browser that requests, receives and displays the web object. The server is the web server which sends the objects in response to the requests. So, this is what we have in the HTTP protocol. When we talk of HTTP, there are different versions of HTTP available. We talk of HTTP 1.0 version, which is proposed in the standard RFC 1945. Then this has been followed up by HTTP 1.1, which has appeared in the RFC 2068. So, these are the standards that are used for this HTTP protocol. Now, to look at how the HTTP protocol works in detail, let us first start with what is the transport layer protocol that it uses. It uses the TCP protocol. So, let us look at how it uses the TCP protocol. So, when we have a HTTP protocol being used, an application, a client process initiates a TCP connection, that is, it creates a TCP socket to the server at port number 80. Now, port number 80 is supposed to be the standard port for the HTTP server. So, a client initiates a TCP connection to server port number 80, wherever the server is located. The server accepts the TCP connection from the client. Remember, the TCP uses a three-way handshake, so this will take place. Then HTTP messages are exchanged between the HTTP client and the web server. So, the HTTP messages are the application layer protocol messages and they are exchanged between the browser is the HTTP client, and the web server, which is the HTTP server. Once the messages have been exchanged, then the TCP connection is closed. So, you can look at the process here. We initiate a TCP connection, the server accepts the connection, then messages are exchanged. Once it happens, the TCP connection is closed. Looking at further details of the HTTP protocol, the HTTP protocol is said to be a stateless protocol. Stateless in the sense that the server does not maintain any information about past client requests. It maintains no information about past client requests. What do we mean by that? That is, every single request is treated as an independent request and a response is given to that. The HTTP server does not keep track of the fact that, oh, this particular page was requested earlier, does not keep track of that. Okay. So, HTTP is a stateless protocol. Now, the problem with protocols that maintain state are typically that they are complex. So, HTTP being a stateless protocol becomes a very simple protocol. That is the reason why HTTP chooses to use a stateless approach. Now, protocols that maintain state are complex because they need to maintain some past history. That is what we mean by state. It needs to maintain some state, some information about what has been happening so far. So, some state has to be maintained, and if the client or the server crashes, then their views of the state may be inconsistent and that will have to be reconciled. So, this makes stateful protocols a little complicated, but HTTP being a stateless protocol is a simple protocol to use. So, if you look at HTTP connections, we said that HTTP uses TCP protocol and it will establish a connection and then it will close the connection. When it establishes and closes connections, there are actually different ways in which HTTP operates. HTTP has an option called non-persistent HTTP or persistent HTTP. So, let us first look at this non-persistent HTTP. In non-persistent HTTP, what happens is at most one object is sent over a TCP connection. Remember that a single HTTP page or web page that is retrieved will actually have some base HTTP content, base content, and it will have some objects embedded in it. So, with non-persistent HTTP, what happens is for every object that is to be retrieved, you will have to have a separate TCP connection established. So, we say only one object, at most one object is sent over a TCP connection. The HTTP 1.0 version uses non-persistent HTTP. Okay. On the other hand, if you look at persistent HTTP, multiple objects can be sent over a single TCP connection between the client and the server. HTTP 1.1 allows for persistent connections as the default mode. It can also work in a non-persistent mode. Okay. The advantage we can see of persistent HTTP is that you do not have to be again and again opening and closing connections. So, naturally it will become faster. So, that is the idea that is used in persistent HTTP. So, if you look at non-persistent HTTP, let us just look at how that will work. Suppose the user enters a URL www.someschool.edu/somedepartment/home.index. Assume that this page contains text and references to some 10 JPEG images. Let us look at the steps that will be involved. So, HTTP now, the HTTP client will initiate a TCP connection to the HTTP server at www.someschool.edu on port number 80. HTTP server at the host is waiting for this TCP connection at port number 80. It will accept this connection and notify the client. So, the HTTP client then sends the HTTP request into the TCP connection socket, and the message indicates that the client wants the object somedepartment/home.index. The HTTP server now receives the request message, forms the response message containing the requested object and sends the message into its socket. The HTTP server now will close the TCP connection, and the HTTP client receives the response message containing the HTML file, displays the HTML file. Parsing the HTML file, it finds that there are 10 reference JPEG objects. So, again the steps 1 to 5 are repeated for each of the 10 JPEG objects. So, you can see that it is a time consuming process. So, if you look at the response time, we normally model the response time in terms of RTTs or round trip times. So, you can see the time that it takes. To initiate a TCP connection, it takes up 1 RTT. Then to request one file, it takes up 1 RTT. Now, if there are, and then we will close the connection, which will take up 1 more RTT. So, 3 RTTs will be taken for every single object, and if there are 10 such objects to be retrieved, it will take 30 RTTs for the connection to take place, for the entire data to be received. So, this so we will just quickly look at how we define an RTT. RTT, as I said, is round trip time. So, it is the time to send a small packet to travel from client to server and back. So, response time we say is 1 RTT to initiate a TCP connection in the case of non-persistent protocol, 1 RTT for HTTP request and first few bytes of HTTP response to return, then the file transmission time. So, the total will be 2 RTT plus transmit time, and this is, remember, this has to be done for every object. So, if you have 11 objects, the initial file plus 10 objects, so 11 into so many RTTs before you get the file displayed. So, that is what happens in non-persistent HTTP protocol. In persistent HTTP protocol, we basically try to address this problem of taking a long time in non-persistent HTTP. So, the issues that we have in non-persistent HTTP are the following. It requires at least 2 RTTs to retrieve the object, then of course, you also need to close the connection, which may take up 1 more RTT, and there is an OS overhead for each TCP connection. Typically, how browsers handle it is that they often open parallel TCP connection to fetch the different referenced objects. That is one way of looking at it. The other option is the persistent HTTP. Here the server leaves the connection open after sending the response, and subsequent HTTP messages between the same client and server are sent over the open connection. So this is what we have in persistent HTTP. So again in persistent HTTP we have two modes of operation. One is without pipelining and one is with pipelining. Without pipelining, the client issues a new request only when the previous response has been received. So you will require one RTT for each referenced object. With pipelining, what happens is the client sends requests as soon as it encounters a referenced object, and as little as just one RTT will be required for all the referenced objects. That is, back to back it keeps sending out the requests and gets a response simultaneously. So this is the mode that we have. So typically the default mode that is used these days is persistent HTTP with pipelining, and with that we are able to get good response time as we see in most of our requests. Okay. So to summarize, what we have looked at today are application types and requirements, how to choose a transport protocol for a given application, and then we looked at an overview of the HTTP protocol which is used in the World Wide Web. Now in HTTP we saw that it is a request response based protocol, and that there are two types of two modes of operation, persistent and non-persistent mode of operation. A few questions to review the content covered today. So what is the primary function of the application layer? Question number 2, give an example for each type of network application. Question number 3, which transport layer protocol is used by internet telephony? Why? Question number 4, what is the HTTP protocol used for? Question number 5, what is meant by persistent HTTP? We will take a look at these questions, and if you are able to answer these questions, you would have understood the content today. Thank you.